Okay, so real analysis 2, the video that I think quite a few people have been waiting for. I've noticed my analysis videos seem to be much more popular than anything else, so I imagine this should be a good video for you guys. But yeah, I sat this exam earlier this week. I can't remember exactly what day. Was it on Tuesday? I really can't remember. I think it was Tuesday, yeah. But yeah, pretty much this went better than I thought it was gonna go, to be honest. Yeah, I was really scared for this one, especially because I remember saying in lectures only half understanding what's going on. So yeah, let's start in. I think again what I'll do is I'll just show all the questions first. Also, this crease is from like me accidentally putting my laptop on this a couple days ago and it never really folded out. Apologies for that. But yeah, that's the first question. I'll quickly flash it up. You can pause and read, then I'll just go through everything again. I was actually supposed to start studying now. It is currently, what is it? 8:56, but I thought I'd quickly do this video since it's well overdue. And then on the final page is that. Okay, so let's get into this, shall we? All right, question 1. Let f map real numbers to real numbers be a differentiable function which satisfies these conditions. Show that there exists psi in the real numbers such that phi prime f prime of psi is equal to 0. Now, for this one, for 1a, normally, I noticed that in the past papers, 1a normally needs mean value theorem, but I had no idea how to apply that to this one, seeing as you only have the limits as x goes to infinity, not like actual values there, and I was unsure if I could actually still apply those, seeing, you know, infinity isn't a real number. Big shock. But yeah, I then contemplated intermediate value theorem. Then I thought to myself, oh, what would I even do with that here? And I didn't have it on my cheat sheet either. Oh, speaking of cheat sheets, I'll quickly talk about what I had on mind for this actually. Forgot about that. And again, this is also creased up about 22 times because my laptop made it its personal mission to just ruin everything. But yeah, here's what was on there. So I had a Rolle's theorem on there. I had an example of using harmonic series for comparison tests just there. This is an example of using what? Oh yeah, a question that you'll see in a second where this kind of question came up, but using the fundamental theorem of calculus and chain rule to like rewrite an integral, pretty much. Taylor's theorem there, mean value theorem there, Weierstrass test right there, an example of using it. Upper and lower Riemann integrals, I couldn't bother to write it down, so I just took a picture. Poor choice because it did not work there. That's supposed to be the Leibniz test, but I couldn't read that in the exam. It didn't come up, thank God. A solution for, wait, what? What was this? Oh yeah, Taylor's theorem, example question. Oh yeah, the upper and lower bounds of the Riemann sums. What else we got here? Oh yeah, uniform and pointwise convergence. Example there. The formulas for the upper and lower sums. Primitive definition along with something else. Wait, my lecturer said that this is the fundamental theorem of calculus 1, the first one, and this is the second one. This didn't come up, thankfully, because like, oof, yeah, it would have been a bit sticky on that one. I haven't really practiced it. Then on here was just something I scribbled down like an hour before the exam, if you want to focus. Oh yeah, but did I not write that already? Oh yeah, I did. Anyway, but yeah, and this was just for the limit comparison test. If you have f over g, then if the limit equals 1, which always does in this exam, then f converges if and only if g converges. Just want to remind myself of that. But back to the questions. Yeah, this one, after the exam, I asked what people did. I had someone say they'd used Rolle's theorem. I had someone say they used intermediate value theorem, I think mixed with the mean value theorem for 1A. Yeah, the person that said that is by far the best real analysis in the class, so I imagine that's correct, but I skipped it like a real man. 1B, let f be a twice differentiable function which satisfies this. Show that there exists a number such that. Okay, for this one was just a simple Taylor's theorem one. This kind of question has appeared in quite literally every single of the past papers, so I knew this was going to be on here. It's just a simple case of, okay, what's my x, what's my h, and what's my y. So yeah, I think this one you just have to set h equal to y, x equal to 0. And then, yeah, it's not too bad on that one. And then here, consider the function f of x, which is 0 between -1 and 0, a half at 0, and then 1 between 0 and 1. Estimate from below the lower Riemann integral of f over -1 to 1. Estimate from above the upper Riemann integral, and decide whether f is Riemann integrable, in which case also compute the integral. This one, I was happy with this one, you know. I remember looking at a past paper and seeing a Riemann integral question where basically from the bounds -1 to 1, it was completely 0. It was identically 0 except for at the point x equals 0, where it was some positive number a. And that was a bit weird to me because when I would set up my partition and compute the sums, I wouldn't know how to show that the upper integral is in fact 0 on that one. But thankfully we have all constant values, so that was nice. Wasn't too bad. I think the partition I chose was -1 minus epsilon over 2, and then 1. Yeah, that was a nice 4-part partition. This question wasn't too bad. In the end, I got the integral to be 1. Oh, pardon me. I got the integral to be 1 because it is quite literally just a 1 by 1 box here. So I like that. Not too bad. Okay, question 3. Let fn be the sequence of functions fn given by show that there exists a function f such that the sequence converges pointwise to f on R as n goes to infinity. One note I just want to mention is that I remember during lectures and even in the revision lecture, like about 3 weeks before the exam, my lecturer made it a point to emphasize that pointwise convergence is useless. Now I can't exactly remember why, but I think it's because something to do with not considering all cases, I believe. I could be misquoting him extremely hard, so if that's wrong, don't take it as my lecturer being wrong. Take that as me not remembering correctly. Does this want to focus? Oh my, sorry about that. Yeah, take that as me remembering completely wrong, but yeah, he said uniform continuity is useful, pointwise not so much. But yeah, this was actually a bit of a curveball because normally there's like a plus n in the in one of these like parts here, so that you can say, okay, when n goes to infinity, this goes to infinity, therefore, you know, uniform can't happen. But that kind of didn't go as planned. Let's talk about pointwise first. Hold on. Pointwise, yeah, of course, you just as n goes to infinity, this goes to 0, so you just show that. I think I took the mod of fn minus f as n goes to infinity. Yeah, that got me the answer. Now, of course, trying that for this one, you would think that it does converge uniformly, as when n goes to infinity, that goes to 0. But I think instead, what I said was the fact that, okay, hold on. I tried like kind of roughly sketching the graph, and I thought, okay, no matter what like fixed value n becomes, n is, then x to the 4 is still you know a like an increasing function. You know, it's a quartic function, so there'll always be a part that at some point will tail off and just shoot up to the sky. So I kind of talked about that, but then I thought to myself, hold on, the question says as n tends to infinity. So I'm just thinking, was I just waffling? That might have just been a bunch of yap, but hey, all we could do is cross our fingers at this point. I'm sure that the sequence converges uniformly to f on AB as n goes to infinity for any fixed interval, my word, AB in R. What do I do for this one? This like whole kind of question has appeared several times in like past papers and in quite a few of the problem sheets. So it wasn't really like a hard question to answer. I just remember what I wrote. I think I just used I think I just took the supremum of the Fn minus F, and then I took I remember being kind of conflicted because I thought, okay, hold on, do I look at cases where the zero part is included as well, or do I just consider the case of where x to the 4 is also being looked at? Because I thought, with supremum, okay, does it mean like a and b such that fn of x is at its max value, so x to the 4 with this part here, or does it mean for any real interval, negative or positive, do I look at the do I have to consider both cases where this bottom part is included and where this is included, if that makes sense? I figured for 7 marks I wouldn't have to, especially because for the problem sheets we haven't had to do that just yet. I could be wrong, I don't know. Question 4. Determine whether the improper integral converges or diverges. Justifying your answer. The creases are really showing now. This wasn't too bad. This one, I don't think I had an example on my cheat sheet of this, but I've done a question similar to this so many times I didn't think I need it. What I ended up doing was using the limit comparison test and comparing it to 1 over x squared. You can effectively take a factor of x squared out of this, and you get, I think, is it 1 plus 2 over x squared all over, is it x squared plus 4x to the, I could be waffling here, but yeah, I ended up I remember being able to take a factor of 1 over x squared out of this, and then I used the limit comparison test, f over g, to show that this does in fact converge, because 1 over x squared converges, comparing that with the harmonic series. This is the question I was talking about earlier, where I had to use the fundamental theorem of calculus and the chain rule. In past papers, there's normally not not in like another function. Like it's normally just this fraction and then these limits. Seeing a cos there did kind of throw me off, but I thought, okay, hold on, that shouldn't really change anything. But yeah, this question wasn't too bad. What I found interesting was the fact that it says show that f is differentiable and compute f dash. Now that's normal, but it also normally says, without explicitly calculating the integral, compute f dash. So yeah, that was an interesting one. Let fn be the sequence of functions given by that. Show that the sequence of f such that the sequence fn converges pointwise to f1, 0, 1 as n goes to infinity. Now this kind of question I've seen about 2.3 billion times. This was just fine for me. I had an example of it on my cheat sheet. The only difference was that on here I think it was x squared plus n. So yeah, there's literally the exact same question, pretty much. So it was just copying that solution I had on there and putting it on my piece of paper, but being careful not to be stupid and write x squared instead of x. So yeah, actually let me walk through this if it's actually readable on here. Okay, you can. So yeah, of course in this instance I said that f goes to 0 for x equals 0, and then x for 0 to 1. These are quite like minimalistic answers, so I doubt if I wrote just this, I'd get full marks. But yeah, I just showed that at x equals 0, fn of 0 goes to 0, is equal to 0, which goes to 0, which is the same as f of 0. Then for 0 to 1, fixed, for x in 0 to 1, which is fixed, I let n be greater than 1 over x. Then for all n greater than that capital N, fn of x equals x. Just making sure that we're in this part of the function here. And then taking the difference between those two, fn minus f, and the modulus of that, we get 0, which is less than epsilon. Point-wise proven. Uniformly showed that when you basically when you plug in that, basically when you take the supremum of the whole interval and plugging in 1 over n will not make this difference 0. You get n, which of course does not go to 0 as n goes to infinity. And then yeah, and then the last question was show that for any fixed a in 0, 1, the sequence converges uniformly to f on a1 as n goes to infinity. Similar steps really. For any a in 0, 1, choose n such that n is greater than 1 over a. For n greater than capital N, fn is x in this instance, and then again just supremums. Not too bad. That was a good question. Now for section B, like I said before, you normally only have to answer 2 questions, but I think I did a 3rd question just to be sure. Yes, I did this one. This was just fine. So consider the power series, show that the function f given by that is indeed well defined, namely that the series converges for any x in 0, 1. Now for this one, what did I use? Oh, I used the theorem where it says that for that I think it said that if the series of upper bounds converges, then it converges itself. I think, did I write on here? Yeah, that's basically what I wrote. Of course, instead of writing 2 to the minus n, I said 3 to the minus 10n. But yeah, because x cannot be greater than 1, and this is an increasing function, I'm saying x equal to 1 gives you an upper bound for that. And then this series 3 to 10n minus 3 to the minus 10n converges. So by the Weierstrass-M test, f converges. So that f is continuous on 0 to 1. Now, in past papers, my lecturer simply said that f is continuous because this is continuous, like what's in the summation is continuous, and left at that. And I thought, hold on, for 6 marks, can it be that? But I just wrote that. I didn't know what else to say on that one. And then for the final part, if I can get my hand to work. Did you set the function f is Riemann integrable on 0, 1 and express its integral as integral 0 to 1 f as a series? So yeah, I just said that it's Riemann integrable because it's a continuous function, and then yeah, it was just simply integrating what's in the summation pretty much, and then I'm plugging in the limits of 0 to 1. I think in the end you get like what was it? I think you get 3 to the minus 10n over 3n plus 1. Yeah, because you get a 3n plus 1 from adding 1 to that and dividing by it, adding 1 to that power and then dividing by it, and then the 1 to 0 makes the x go away. So yeah, that's that exam. Went better than expected, to be honest. I thought it would be terrible because analysis is not my strong point, as I'm sure you guys have figured out by now. A bit of a longer video, but yeah, that's it for this video. Hope you enjoyed.